Good afternoon, everyone. I hope you and your loved ones are healthy and safe. My name is Randy Bell, and I'm the director of the Global Energy Center at the Atlantic Council. Thank you all for joining us for EnergySource Innovation stream today, where we aim to highlight new energy technologies with the potential to reshape the global energy system. I hope you all enjoyed our new innovation stream theme music, written by Alex Kokova, the brother of our Global Energy Center colleague, Olga Kokova. Thank you so much, Alex. Today, we'll be hearing from Dr. Michael Weber, Chief Science and Technology Officer at ENGIE, and also the Josie Centennial Professor at Energy Resources at the University of Texas at Austin, where he is calling in from today. Michael will be speaking about the new technologies necessary to optimize the production and utilization of low carbon gases across the global energy system. Before we get started, two administrative details. First, you can follow us on Twitter at AC Global Energy and use the hashtag InnovationStream. Second, after Michael's presentation, you can submit questions through the Q&A function on Zoom, and I'll try to get to as many of these questions as I can. If you are watching on another platform like YouTube, unfortunately, we can't take your questions. So please let me welcome Michael Weber to the Atlantic Council. Michael, thank you so much for joining us today.
Thank you for having me. It's my pleasure. I appreciate the opportunity to be part of the conversation.
So Michael, you've had a very interesting recent experience with COVID-19. You've been in the news for reasons other than your fantastic research and writing. Perhaps you could just tell us a little bit about that experience.
Sure. So it's a multi-part story, but the short story is I tested positive for the antibody for coronavirus just a few weeks ago. So in mid-April, I found out I had coronavirus, which makes sense actually, because I had a very weird sickness in early to mid-January that made me feel horrible, that I was pretty sure wasn't the flu, but never knew exactly what it was. This explains it. So I probably picked up the coronavirus somewhere in my international travels, but potentially the Consumer Electronics Show in Las Vegas in January, because that's 170,000 people from around the world, dozens of countries represented. And I probably shook hands and was in the airspace of many thousands of people. So maybe I picked something up then. And there's been several news stories about this because this pushes the date of the arrival of coronavirus in the United States much earlier than people thought. And I hate to think I'm a super spreader, but maybe I was a super spreader, or at least I was at a super spreader event of some sort. So that's been getting some attention in the news the last week or so.
Well, we're glad you recovered. We're glad you made it through that okay. It sounded pretty awful. How did you get? I know you were in Paris for a while, and then you came back here to the United States. How did you get here? What was that like?
Well, it was 8 weeks ago today that my wife and I and our youngest evacuated from France. We were in Paris, where I'm based, working at ENGIE as Chief Science and Technology Officer, as you mentioned. We were there and we saw what was happening in France with the rise in number of cases of people who were infected or dying from coronavirus. And it was just 8 or 9 days behind what was going on in Italy. So we realized we probably needed to get back to the States to see my parents. I've got a mother who's at risk and my wife's mother's at risk. We thought we need to see them before there are any lockdowns in place. So we thought we'd fly back to the States for a couple of weeks or something. Then we got a call. This was on March 12th in the morning at 2:30 a.m. Paris time from my daughter, who said, Trump is closing the borders. What are you going to do? So we ended up doing a middle of the night sort of escape where we each grabbed a bag, turned off the radiators, threw away the perishable foods, bought same-day tickets, and flew home that day, March 12th, 8 weeks ago. And of course, since then, there have been international travel bans and lockdowns, things like that. So we haven't been able to get back. But it was a middle of the night evacuation. So we just grabbed a bag and I grabbed 5 shirts that have collars and 5 T-shirts. And that's all I've been living with for the last 8 weeks. And it was kind of crazy. And we weren't the only ones. A lot of Americans showed up at the airport that morning to catch a flight home. And since then, it's become more difficult. So we're riding out the pandemic in my hometown, Austin, Texas. This is my home. And hopefully we'll get back to Paris soon.
Wow. As we were talking about before this, I think we could have this whole call be just about your experiences with COVID-19, because it's been fascinating and a little bit harrowing at times, but also hilarious at times. So, but we will not do that. We're here to talk about low carbon gases and the energy system. So why don't we get started with what you want to talk about, and then after your brief presentation, we will go to Q&A.
That sounds great. So I'll just give some opening comments to set the stage and give some background information that might be of interest to people. And I'll start by introducing ENGIE. Not everyone knows ENGIE. ENGIE is a large energy and infrastructure services company based in Paris, France. That's where I serve as the Director of Research and Innovation, or the Chief Science and Technology Officer. The company has about 170,000 employees in 70 countries and has over 60 billion euros a year of revenue. So it's a large company. In the United States, it's one of the largest companies that no one's ever heard of, I like to say. Much better known in Europe, especially France and Belgium. We have three main businesses at ENGIE: electricity, gas, and services. And services is very much prioritized on energy efficiency. We actually are the world's largest independent electric company in terms of installed generating capacity. We have over 100 gigawatts of installed capacity. The only companies that are larger tend to be the state-owned ones in Russia or China or elsewhere. So we're a very large electric company, but we're also a very large gas company. A little over half of our capacity, or about half our capacity, is natural gas power plants on the electricity side. But then we also run the gas networks in France and Turkey and Brazil. So we're a big electric company and a big gas company and a big services company. As a publicly listed company, we have to make a profit. We're answerable to our shareholders. We have to make a profit, but we also have some internal mandates as a company that are philosophical. We must decarbonize. That is a mandate from our board and from our CEO, and it's been that way for years, that we as a company must make a profit, but we must decarbonize. We have other mandates as well. For example, we're aiming for gender balance among our managers, so 50-50 balance between men and women in our managerial ranks by 2030. We're already making progress. We've made some good progress in the last few years. So we have a variety of mandates that we have to implement in addition to our requirements to make a profit. And that creates context for the research innovation part of the company. Is the research, or what are the advances we have to make so we can comply with those mandates while making a profit? We have a large research lab in Paris called Cogen, and another one in Belgium called Laborlec, plus some other smaller labs around France and Singapore and Chile and different parts around the world. I think this is sort of the sort of ecosystem I work in. So we're working on this now, and we've already had some success. We have already decarbonized our power by 50% in about 3 to 4 years. This is incredible. Our carbon emissions as an energy company from the power sector have gone down 50% in just 3 or 4 years. And in some ways, that was, I want to say, easy, but kind of obvious. Keep your nukes, sell or shut down your coal, keep your gas, build wind and hydro and geothermal and solar as much as you can. So we've done the easy part of power. The next 50% will be much harder because those are our natural gas plants. And we have to think about our 50 plus gigawatts of gas plants. We might be the world's largest owner and operator of natural gas power plants in the world. What do we do to decarbonize those gas plants? So that remains an open question for us. And next, how do we decarbonize our gas networks? I mentioned we have the gas pipelines and networks in France and Turkey and Brazil and elsewhere. Well, if we need to decarbonize, we have to decarbonize the gas system. How do we do that? And frankly, that's harder than decarbonizing the power sector because the solutions aren't as mature, aren't as obvious, and they aren't ready to go quite the way they are with, say, wind and solar in the power sector. So what are we going to do if the gas problem? Let's decarbonize gas. There are a couple things we can do. The first thing, let's say we use this much gas. Let's implement as much efficiency as possible so we use less gas. Let's make the task easier by using efficiency to reduce demand. That's end-use efficiency, compressor efficiency, burner efficiency. Every place we use gas, we should use efficiency so that we can get the same services and same qualities we want from the gas that are still delivered, but using less gas. So efficiency is the first thing we have to do. And efficiency usually pays for itself. And that's why we have an energy efficiency services company. And we're doing this for large buildings and college campuses and hospitals and different facilities, working on efficiency to make the problem simpler. And we do that for electricity. We can also do that for gas. So start with efficiency. Next, you should electrify what you can. There are some loads that are served by gas or some services that gas provides that could be provided by electricity instead. I'm thinking some obvious things, or if we broaden the view to include fuels, light duty vehicle transportation could be electrified. Water heating and space heating and building heating could be electrified. Cooking could be electrified. Some of these are pretty easy, so we should electrify what we can, especially for new construction. That is an option. But not everything can be electrified easily. There are some things that are hard to achieve with electricity. In particular, I'm thinking like industrial heat, where you need a lot of heat in one place. Fuels are a great way to get that heat. Electricity is not always the best option in those cases. Aviation, you need fuels. Heavy duty shipping like trucks or marine, often you need fuels. And then households and businesses where you already have gas appliances and gas lines, it might be non-trivial. It might not be cheap to swap out your gas appliances for electric appliances. For a household, that could cost several $1,000s of euros to swap out your water heaters and your stoves and things like that. And for a larger house, could easily be $10,000. For a business, much more. So the technology exists, but maybe we don't have the money, and so it starts to become difficult to electrify in those retrofit situations. So then what do? So you do efficiency first to reduce the hurdle, then you electrify some, but you still have some gas that you need. I don't know, maybe that's half the demand. Maybe half the demand we can satisfy with efficiency and electrification. What are we going to do with the rest? Well, there are a couple different options. You can use conventional gas with carbon capture, where you scrub the CO2 at the smokestack. You could use conventional gas with offsets. In that case, an offset means you're capturing carbon somewhere else. Instead of carbon capture at the smokestack, you might plant trees or do soil management or do direct air capture or something somewhere else to take CO2 out of the atmosphere, and that offsets the CO2 you emit from your use of gas. Or the third option is to integrate low carbon gases, to replace the gas you're using now with a low carbon version. And fundamentally, that's the question we have to solve. We either need to replace the gas infrastructure or replace the gas in the infrastructure. That's the option for us. I want to talk about that last one because that's the most vexing problem. And that actually defines a lot of the research agenda for us at ENGIE is how are we going to do this? Do we need to replace the gas systems or do we need to replace the gas in the systems? What are those green gas options? Hydrogen. Hydrogen's been in the news. Hydrogen's been around the corner since the middle 1800s. We're getting closer. Any day now we'll be there. Hydrogen's very attractive because it's clean, it's light, it burns clear, it burns hot, it opens up efficiency opportunities. You can burn it or use it in the fuel cell to get electricity directly. So hydrogen's really a great fuel. It's very versatile. We can use it in many ways, but hydrogen's hard to make, it's hard to move, and hard to store. So these are the challenges. And we're used to the world of gasoline or diesel or methane, where it's very easy to move it around, easy to store. You can put gasoline in a tank and come back to it years or decades later. It's still gasoline. You can move methane many thousands of kilometers or miles. It's easy to move, easy to store in tanks and caverns. So what do we do with hydrogen? Hydrogen's much harder. We have been trying. So we make hydrogen at ENGIE and we put it into pipes and we move it. In fact, we set the world record in Dunkirk. We blended 20% of the gas mix in pipelines was hydrogen. That's really exciting. By the way, about 6 months later, the same demonstration was done in England, and they got a lot of press as the first company in the world to blend 20% hydrogen into their pipelines. And we got very frustrated at ENGIE because we had done it many months before. And maybe this is the England-France rivalry. We didn't get the press they got. So we're trying to make amends and make people aware that we've been doing this. It's kind of cool to blend 20% hydrogen into your gas pipeline. That's great news. However, that's only 6% by energy because hydrogen's so light, the volume it displaces isn't a one-for-one on energy. So it's good news, but doesn't solve all our problems. And as we go to higher fractions than 20% hydrogen, you start to have to worry about things like changing out your burner tips or swapping out your turbines, different blades, different materials. There are metallurgical effects or metal degradation effects in the pipes. You have to worry about leaks. So hydrogen in the pipelines is all solvable, but is non-trivial. It will take some effort. So that makes us think of hydrogen carriers, things like ammonia, formic acid, methanol, things that have a lot of hydrogen that we can move instead. And so we're doing work on that right now. We're looking at using ammonia for storing offshore wind. It's hard to move the electricity from this offshore location, but we can use electricity to make ammonia, then move the ammonia instead. So that's one option. We're using formic acid as a carrier for hydrogen. We have a demonstration in Dunkirk with a steel mill from ArcelorMittal. We take their blast furnace gas, waste gas, turn it into formic acid. Formic acid can be turned into dimethyl ether, which can be used as a replacement for diesel. We're working with Volkswagen to burn it in their engines. So we're looking at hydrogen carriers. I think that's very exciting. But all of these hydrogen and methane alternatives require new investments. Think about it. If we want to replace our gas system, that means new hydrogen pipelines or hydrogen carrier pipelines, new compressors, new storages for tanks or caverns, new burner tips, new water heaters, new power plants, you name it. And so that becomes pretty expensive, and this is on our minds. If you look around the world today, the methane infrastructure, the natural gas infrastructure, the replacement cost is like $40 trillion. The depreciated value is like, I don't know, $10 trillion. So there's $10 trillion of steel in the ground for the world's pipes, compressors, storage, and power plants that run on natural gas. So we have invested a lot of money, a lot of capital, and a lot of equipment that already exists that runs on methane. And that makes a very expensive question for us, because if we want to replace that methane infrastructure with a hydrogen infrastructure or an ammonia infrastructure or something else, it's probably going to be more expensive than the methane infrastructure, because the natural gas or methane infrastructure has a very mature supply chain. It's over 100 years old, but there are many options, a lot of competitors. The prices are very, very good. It's very robust. So this raises the question, well, do we have a way to use the existing methane infrastructure, or do we have to replace it? And so we're focused on drop-in fuels, things we can use for the existing infrastructure. So what are the drop-in options for methane? One is biomethane, methane from natural resources, renewable sources. This is like food waste or sewage or crop waste or manure, different places where you have organic waste you can decompose anaerobically into methane. This works great. It's universally available. However, it is limited in scale. Typically around 10 or 20% of the world's gas demand can be provided by biogas. It's also geographically variable. There are some places in Europe, say small towns in Germany, that have more cows than humans and therefore a lot of manure. The manure can make enough biogas to serve all the town's needs. You can meet 100% of the town's needs for heating with gas from biogas. But there are other places like the Middle East where there's not a lot of organic matter and the needs for gas are quite high for electricity. You can't quite get there. So biogas is limited in scale, but it's attractive for some part of our needs. So this takes me back. If we have our needs here, you go efficiency, electrification, biogas, you still have some part left over for gas that we need to find a solution for. Maybe gas to capture, gas offsets. What's that last bit? Well, there we can have synthesized renewable methane. We can make methane. If you can make hydrogen, you can make methane. You can get hydrogen from water or water vapor, get carbon from carbon dioxide, and we have too much carbon dioxide, so we should take it out of the atmosphere. And then you recombine it into methane, and then you can drop that into the fuels. You don't have to replace the power plants, the pipes, compressors, or the burner tips. So that's the opportunity. This works. We already do it. We know how to do it, but it's expensive. It's plagued by inefficiencies. And so therefore it's not the cheapest option. And that becomes the research agenda for us. How do we in research drive down the cost of making methane from hydrogen? That's the opportunity. That's where we're focused. And that's what we're thinking about. And this looks particularly appealing because we're overbuilding wind and solar right now for other reasons. We like wind and solar, but they have a variability. So we overbuild. We might have excess electrons available, and we can convert those excess electrons into molecules and make them more valuable in the process. In summary, I'll stop in just a second so we do Q&A. In summary, we have to make a question. We have to answer a question of whether we're going to replace the gas infrastructure or replace the gases. And if we're going to replace the gas infrastructure, it will be expensive and it will take decades. So we better get started. If we're going to replace the gas in the infrastructure, it saves us time. It might save us a decade or two. It lets us leverage existing investments, so it might be cheaper, but there are important technical hurdles we have to overcome to get there. We better get started there as well. So I'll stop there. Thank you so much. We got time for questions. I'd love to hear what you want to hear about, and then I'll do my best to answer them.
Michael, thank you so much. That was really fascinating, and you combined a lot of different topics into a very concise lecture. Are you a professor by chance?
I'm a professor. It turns out I like to give lectures to people. Yeah, absolutely.
Yes, that was fantastic. We already are starting to get a bunch of good questions in the Q&A. For those on the line, be sure to ask your questions through the Q&A function. That's what I'm monitoring right now. Of course, I have a ton of questions. I'm only going to ask one. Because I think we're going to have way too many coming from the audience. But mine is about the amount of power that you need to generate, whether it's hydrogen or synthetic methane or whatnot. I was in a meeting with a chief technology officer of a major international oil firm last year. They mentioned that if you wanted to just produce the amount of ammonia that is demanded in the world right now, so think of ammonia as a stand-in for hydrogen. If you wanted to produce that in green ammonia, it would require all of the installed renewable capacity in the world at the end of 2018. So we've installed more since then, but you're still talking a huge amount of power to produce all of that ammonia. We went and ran that math, and we came up with basically the same number. So, how do you think about when you're producing this methane or hydrogen or whatnot, what power is going into it, and how you make sure that power is clean or that production process is clean?
That's a great question. And by the way, these numbers are astounding when we do the math, like you just mentioned. So we already have a hydrogen economy. We have a hydrogen economy because hydrogen is used for semiconductor manufacturing. It's used for steel mills. It's used for petrochemical. It's used for refineries. And the hydrogen is used, for example, to lighten and sweeten heavy crudes, to make them into gasolines, useful things. So we already have a hydrogen economy. And we already have an ammonia economy, a hydrogen carrier economy, ammonia almost exclusively for fertilizers, but there are other chemical uses and even weapons and munitions and things like that. So we have hydrogen and hydrogen carrier economy. And for both of them, primarily it's made from natural gas to solve that problem you mentioned, which is it takes a lot of electricity to make ammonia or to make hydrogen, and natural gas is cheap and abundant, and there aren't rules everywhere yet for the carbon emissions, so it's okay to use natural gas and that kind of thing. If we just want to build the electricity to make the ammonia, it ends up being a lot. So let's put some numbers on it. The world's electrical generating capacity that's installed today is about 6 terawatts. That's about 6,000 gigawatts or 6 million megawatts. So let's say there's 6 terawatts. About one of those terawatts is just in the United States, about one's in Europe, that kind of thing. So we have 6 terawatts, and that is overbuilt a little bit. We tend to overbuild our electricity system by 10 to 20% for reliability purposes in case the power goes out in one place or a power plant goes down or that kind of thing. So we have 6 terawatts. If we want to go to all renewables, and wind and solar are a big part of those renewables, and they're variable, they change by the weather and the position of the sun relative to the earth and that kind of thing, we will have to overbuild by more than 10 or 20%. Maybe we overbuild by 40 to 80%. So if we want to go to a renewable electricity mix with variable supply, now geothermal and bioenergy and hydro aren't as variable, so it wouldn't all be wind and solar, but we might overbuild by 40 or 80%. So that applies another couple terawatts, a couple thousand additional gigawatts just to satisfy the electricity system. Then if you want to make your ammonia manufacturing, it's hundreds of gigawatts, a significant fraction of terawatt, just to have the electricity, just to make the ammonia. And then it's another, I don't know, a couple hundred gigawatts to just have the electricity, just to make the hydrogen for today's hydrogen demands. But then if we want to make the electricity to replace all of our fuel demands for diesel, for jet fuel, for gasoline, for chemicals, all that kind of thing, then we're talking about another non-trivial number of terawatts. And we can think of a terawatt as $1 trillion. We think of a gigawatt as $1 billion. So for every additional terawatt, it's another trillion euros or $1 trillion. So we get to, I don't know, 2 to 10 terawatts pretty quickly, which means a handful of trillions to $10 trillion. So it gets pricey at one point, which is why alternatives are useful. Okay, let's use efficiency to lower the hurdle as much as possible. Like I said, let's use biogas because biogas is already kind of available from manure and that kind of thing. Let's reduce the number of terawatt and therefore the number of trillions of dollars we need to supply that demand. So I think we can't do it just by building a bunch of electricity and just manufacturing hydrogen and methane. We're going to have to do all these pieces together to reduce the cost and reduce the timelines. And by the way, building that much wind and solar starts to take up a noticeable amount of land. People will start to push back a little bit. That will drive up costs. So they won't always be the cheapest solution for that last 10 or 20% when we have other options available.
Fantastic. So we have more questions than we've ever gotten. And we're not going to be able to get through all of them. I'm going to try to combine as many as possible. But the first one comes from Soli Shin, who was a grad student when she read your energy textbook.
All right.
So you have a fan.
Right.
One.
Did she say she's a fan? She might not be a fan because she read the book. Well, fine. So
I'm just going to assume that she's here because she's a fan.
Okay.
How does climate risk factor into the financial decisions of a company like Engie?
So that's great. So at a company like Engie, we have all sorts of risk. We have financial risk. We need to make sure we make money. We have to worry about hurricanes. We have to worry about floods. We have to worry about explosions. We have to worry about our customers going broke in a pandemic. We have to worry about climate change as well. That's just part of it. And climate change drives a lot of these factors. It makes floods, droughts, and hurricanes more likely. It also has a non-trivial relationship with pandemics. So we have to think about this, and we think about risk a lot. We primarily think about it first in terms of safety. Is our system safe? We don't want our electricity or our gas to hurt anybody. And as we've seen in California, electricity can spark wildfires. And as we've seen also in California elsewhere, that gas can lead to fires or explosions. So there are safety risks. We take this very seriously, as every utility should. A lot of our effort is on safety. And as climate change causes soils to shift or aquifers to get flooded or water levels to rise or the fires to be worse, it makes our risks more intense. We have to prepare for that. One way to mitigate for that is to harden our system, so make our system stronger, more robust. Another way is to avoid the problem in the first place by reducing carbon emissions. And we think in the long run, it's cheaper for society and cheaper for the world and cheaper for civilization to avoid the effects of climate change rather than to adapt or deal with them later. We often think about how expensive it will be to avoid carbon dioxide emissions, but it's more expensive not to avoid them. It's more expensive to let climate change happen. And that's our analysis. And that's why we believe morally and financially we have an obligation to decarbonize. And we price that risk into our projects. It does show up in that it will affect the temperature of our solar panels. Solar panels are less efficient when it's hot, but it might mean there's more sunshine. In some places, it means there's less sunshine. So we have to factor that into our models. It certainly affects our hydro resources. Our water levels are different than they used to be, and that affects how we can predict what kind of power we can get from our dams. So it shows up all up and down our planning. We think about it. A lot of energy companies do. Even the energy companies that don't believe in climate change will start to factor in some of these risks. So they're starting to think about it.
That's fascinating. Okay, a question from Juho Lipponen from the IEA, who runs their CCS program. The reason I'm taking this question right now is that he also complimented my confinement beard. So that's a great way to get your question asked.
Yes.
To, compliment the host. Really, everybody take a lesson. Actually, Juho, this might be coming off in the next week or two. So this might be your last chance to see it. Anyway, he asks, what is Engie's vision for CCUS? How does that sit in your plans?
That's a great question. By the way, I tried to grow a beard and I could not. So I had to shave it off. I couldn't get there. I love that the question says CCUS, right? For a long time, it was CCS, carbon capture and sequestration. And now the latest thinking is carbon capture utilization, U for utilization or use and sequestration. And that's very exciting because we care a lot about the U in particular. We have a lot of carbon emitting processes with our power plants, and we have a lot of uses for carbon potentially. So we're focusing on that U, thinking that the markets will provide a carbon capture solution, that the major engineering firms will provide that solution better than we can. So when it's ready, we'll be ready to buy it and implement it on a few coal plants we have remaining, or on our natural gas plants, or on smokestacks of our customers. We have a lot of industrial customers, and they might ask us to help them decarbonize as they already are doing. So it'd be good to install carbon capture in those facilities. And then the storage, well, we have geological capabilities at the company. We can look at storage, but we think use is better. So rather than landfilling the CO2, maybe we can use it to make plastics or building materials or drywall, or use it for agriculture. We're doing a lot more work in agriculture at Engie than we used to. And who likes CO2? Plants. And they also like input of fertilizers, like ammonia from hydrogen, where we can make that. They also are moving to become more electrified as agriculture moves indoors or has electric tractors. So we're starting to see a big customer for CO2 in agriculture facilities as well as industrial facilities. So we're focused on the U part, and we have a research lab focused on the U, and we think the markets will provide the CC and the S for us. So that's where we are. We're watching those parts, focusing on this one. It's a part of our plan because it might be hard to get to zero carbon without carbon capture.
Got it. Okay. Really interesting question coming from Peter Fairley and Erica Guys. I think it's two people on the same account, but it's how they've inputted their name into Zoom. So how does methane leakage impact your cost analysis for shifting to hydrogen versus synthetic methane? And also think just in terms of from a climate change perspective as well. How do you think through that?
That's great. So leakage is a concern for us primarily as a safety concern, but it's also a concern from a climate angle. So we worry about leakage a lot. And there's a distinction I need to make here between the utility companies and oil and gas companies. So oil and gas companies, the companies that do the extraction, the exploration and production, have much higher leakage rates than the utility companies, the pipeline companies. So the pipeline companies, we have to take the tightness or the robustness of our pipes very seriously, because if you have a leak of a flammable combustible product, it could hurt your customers or cause an explosion or kill people or do a lot of damage. So we have a much lower leakage rate than other parts of the supply chain of the sector because we have different liabilities and different risks. So we already take it very seriously. Add in the climate effects, and we have to take it seriously yet again, because methane is a much more active greenhouse gas than carbon dioxide by dozens, depending on your timeline. So let's say it's 25 times worse. So a small leak can undo a lot of the benefits of using gas to displace coal, for example. So we have to take leaks seriously, first for safety and resilience, but also for climate change, and that factors in. Now, if we go to hydrogen, hydrogen's much leakier. Hydrogen's a much smaller molecule, has a much longer mean-free path. It slips out of pipelines and storage tanks much more easily than methane because it's so much smaller. So you have to really tighten your system much more. And the leak is not a problem from a climate change perspective because hydrogen's not a greenhouse gas that way, but it is from a safety perspective because hydrogen's more flammable, more combustible, and more leaky, which is a challenge. And that's why the hydrogen infrastructure would be more expensive. You have to replace the pipes or add linings, change the seals, change the O-rings, all sorts of things. So it is very expensive to make a leak-free hydrogen system. When I was a PhD student at Stanford in mechanical engineering, doing my research for combustion engineering, we would use hydrogen to find leaks because hydrogen would always find the leak. Now, what does this factor in with synthetic methane? Well, the same concerns you had before with other conventional methane is you don't want leaks for safety reasons anyway. Now you don't want it for climate. So if you have low carbon power you use to make low carbon hydrogen, you use to make low carbon methane, but then that methane leaks a lot, you undo a lot of the benefits. So we have to take it seriously and we build that into our risks. But we already take it seriously even before we got to that point, and we just see more incentive to tighten it up as time goes on.
Michael, thank you. We have so many questions, and unfortunately, we're out of time. We do try to keep these to a tight half hour. I'm not going to get to Chris Brooks' question, but he does say hook 'em horns. So, Chris, sorry I can't get to your question. I just want to thank you so much for being here. We really, really appreciate your time today. It's hugely, hugely valuable to have these conversations. Thank you all again for tuning in. You can follow Michael on Twitter at Michael E Weber and Angie at Angie Group. Hope you'll all join us next week for our next innovation stream, where you can listen to that great music again with Babar Ozden, co-founder and CEO of Mana, who will discuss digitization solutions for the energy sector. That's Wednesday, May 13th at 2 p.m. This presentation is available on the Atlanta Council website, the YouTube channel, Facebook, Twitter, so please do share it with your colleagues. You can always reach out to Michael if you have other questions. I want to thank the entire Global Energy Center team who put this together, particularly Olga Kokova and Mitali Murla, and also the Atlanta Council events team, Jackson Styron, Tom Knoll, and everybody else who helped put this together. Thank you all so much, and we look forward to seeing you next time.
Thank you.